Okay, so we are in an Introduction to Statistical Learning, second edition. We're in chapter 4, and we're on the 10th question in the conceptual questions at the end of the chapter. So here's the question right here. And so it tells us that in the book on page 168, the equation 4.32 derives an expression for this guy right here. Okay, and the idea is that we can use that expression right there to classify observations into one of capital K classes, right? So if we have an observation, the probability, among the K classes, the one with the greatest of this value right here, we would assign that observation to that Kth class. I hope that makes sense. So, and in the book, that expression through a long derivation, in fact, I'll show that derivation here in a second, but we get to this expression right here, where that expression is just this linear model where the A sub k is given by this, and then the B sub k is given by this, and it's multiplied by x, okay? So in the book, just to kind of give you a sense of what's happening here, it's all given right here. Okay. So again, we start with this expression and we work through it in the book, and eventually we come up with this final expression here. Okay. Get rid of that. So now we're asked to derive basically that same thing, but instead of having multiple dimensions, right? P dimensions, we have where there's p equals 1 dimension. So in effect, what that is going to do is that instead of there being a covariance matrix, for instance, among the p dimensions, there's just going to be one variance measure. Okay. So anyway, so we're going to do that in the case where p equals 1. All right. So again, I won't go through the derivation. You can look at the derivation here for yourself. But in the end, we come up with this expression right here as our final one, and then we say that this part is equal to AK, and then that this part right here is equal to BK, and we put it into this form here. But I think maybe what is hopefully being gleaned here is that, so if I call this final expression that we got here, I'm going to call that D, lowercase d. Okay. So here's lowercase d right here. Notice how similar this is to the delta function for LDA that we derived way up in question 2, which looked like this. And so you can go check it out for yourself. Okay. So we have corresponding pi terms, corresponding mu small k terms over 2 sigma squared, and then corresponding x times mu k terms here. The only difference is that for dk, we are always referencing this reference class, mu capital K or pi capital K, right? But it should make sense that these two expressions are very similar because they're both trying to do the same thing. In the case of LDA, again, we are trying to assign an observation, y, to the class for which this value is greatest. And similarly, for what is happening here, we are assigning an observation K, again, to the class that has the largest of this value. Okay. Well, since in the expression for dk, the capital K reference class is going to be the same for each of the small k classes, then it can basically be discarded. And so if we go through and discard all of the capital K references, we come out with the delta function for LDA, and again, that should make complete sense, right? So we can accomplish the same thing with either expression, and so we'd better hope that the two expressions have quite a bit of parallels. Okay, I guess that's all I'll say here.